Thanks very much for your kind invitation to speak with you here today on this important topic of climate change impacts, challenges, and opportunities.
What I'd like to do in the next 30 minutes or so is address these key questions that motivate this talk. First, what exactly do we mean by global climate change and what are its causes? What then are the current and future impacts of climate change that give us concern? And what measures and policies can we pursue to either reduce or avoid dangerous impacts? Finally, I'll speak a little bit on what the outlook is for actions to deal with climate change at a global level. But first, just some very brief background on the fundamentals of climate change for those of you who may not be familiar with it. Fundamentally, it has to do with energy and the temperature of the planet. The temperature of Earth, our planet, is governed by two basic flows of energy. One is the solar energy that comes in from the sun and warms the planet. As the planet warms, the Earth itself radiates energy back to outer space. And the balance between those two is basically what determines the overall temperature of the planet. We also have uniquely a thin layer of gases, the atmosphere, which contains some gases that affect this overall balance between solar energy in and Earth's energy out. The result of that is that these gases act as a blanket to help warm the planet beyond what would otherwise happen if those gases were not there. So what we call the greenhouse effect is due to atmospheric gases that absorb Earth's radiation, which warm the planet, and they are called greenhouse gases. They include carbon dioxide, CO2, methane, nitrous oxides, and other gases in small amounts. And they also include water vapor. Water doesn't accumulate in the atmosphere. It simply rains when there's too much available. The important thing to understand is that if these gases were not there, if we had no atmosphere, we would not be here talking today. The Earth would be a very cold minus 19 degrees Celsius instead of the actual average temperature of about 15 degrees Celsius. So that difference, that 34 degrees of warming, is actually due to the presence of these gases called greenhouse gases at their natural level. The problem is that over the last roughly 150 years, human activities have been increasing the amount of those gases in the atmosphere. This graph shows the trend in emissions of carbon-bearing gases, mainly CO2, from burning fossil fuels. Most of the world's energy, about 85% of our energy, comes from burning coal, petroleum, and natural gas, all of which contain carbon. And when those fuels are burned, they produce CO2, which accumulates in the atmosphere. And here is the evidence for that. This set of graphs shows a 1,000-year history of three greenhouse gases, CO2 at the top, as well as methane and nitrous oxides. And one can see a dramatic increase in the last roughly 150 years since the Industrial Revolution, where we started burning fossil fuels in increasingly large amounts. One of the things that distinguishes these gases from other air pollutants that we are more familiar with is that they are very stable. Once they're in the atmosphere, they are not easily or quickly removed. As I said, there are several gases that are called greenhouse gases that contribute to global warming. This pie chart shows the relative importance of four classes of gases. As you can see, the message here is that the dominant gas by far is CO2 from the use of energy associated with fossil fuels. Most of what I'll talk about today will focus on CO2, but other gases are also involved in this phenomenon. So what have been the current trends? We saw the recent trend in rise of concentrations historically. This is some more recent data. This graph shows the last 40 years of emissions of greenhouse gases from human activities, from 1970 up until 2010. And what we see is increasing levels of emissions, even in spite of actions and activities that have been taken over the past several decades to try to reduce these emissions. In particular, actually, in the last decade of this period, the growth has been even faster than in the previous 3 decades. These emissions are associated largely with the 2 things we love the most: our cars and our electricity. Transportation and electricity generation are the major contributors, about 75% of the emissions, and other activities contribute the rest. As a result of those increasing emissions, the concentrations of CO2 in the atmosphere also have been increasing. This graph shows the data, the trends measured at an island in Hawaii, Mauna Loa, which has been measuring the CO2 concentrations since the 1950s. There is absolutely no doubt that atmospheric levels of CO2 are increasing, and it is clear that those increases are due to human activities. In fact, last year, the CO2 level in the atmosphere reached a level of 400 parts per million, ppm. That is a level that has not been seen since prehistoric times, 11 million years ago. So we are currently living through an unprecedented period of increasing concentrations of greenhouse gases in the atmosphere, the consequence of which are increases in Earth's temperature that have already been measured. The best data and science we have today indicates that the temperature of the planet today is about 1 degree Celsius warmer on average than it was 150 years ago. So when we talk about global climate change, there are a series of phenomena that get increasingly complex, but it all starts with emissions into the air of greenhouse gases from human activities, principally the use of energy, but also other activities, including agriculture and various industrial activities. As a result of those emissions, which have long lifetimes and don't easily come out of the atmosphere, the second box indicates increases in atmospheric concentrations of those gases of the levels that we just showed you. In turn, the higher concentrations lead to higher temperatures, and those higher temperatures produce changes in what we call climate. What is climate? Climate is defined as kind of average weather, technically over a 30-year period. And it includes not only temperature, but other measures of average weather, including humidity, wind, and precipitation, how much it rains, snows, or other forms of precipitation. And because temperature changes drive changes in the larger climate system, those changes will result in impacts, the last box, on ecosystems and human welfare. What are those changes? A group called the Intergovernmental Panel on Climate Change has been studying climate change impacts for over 25 years. Let me show you some of their most recent findings. The main message that comes from the science is that the human influence on the climate system is clear. Those are influences on the atmosphere, on extreme events, on the water cycle, glaciers, and sea level. The other conclusion from the IPCC study is that the observed impacts, the things we can already see today, are widespread and consequential. This is a chart that has documented patterns of impacts that have already happened that are attributed to climate change throughout the world. The blue figures represent changes in physical systems, like changes in ice melting. The green systems represent biological impacts, such as effects on aquatic life, and the red systems represent effects on human systems, such as food production. Here's one example from that last category. The impacts of climate change on the yield of different crops. There is already documented evidence that over the past several decades, climate change is making it increasingly difficult to increase crop yields, which have been the benchmark of food production and increased productivity. It's getting more and more difficult to increase productivity from crops like rice and corn, for example. So peoples, societies, and ecosystems around the world are both vulnerable and exposed to climate in different ways. This picture, again, from the IPCC, this is not a street in Venice. This is a street in New York City, right after the flood caused by Hurricane Sandy several years ago. Devastation of the sort that had not been seen in a city that thought it was well prepared for events of this type. Here's another example, an article from a recent newspaper showing devastation in Alaska of a village, a coastal village, that has decided now, because of the effects of climate change, it's time to move the village away from the coast further inland. Migration of people and property that is already underway. The other hallmark of climate change predictions is that we can expect to see more extreme events as atmospheric concentration rises. By extreme events, I mean the kinds of things we've already been seeing in recent years: hurricanes, floods, drought, fires, things that have affected all parts of the world in different levels of severity. These are the things that will become increasingly more common and more prevalent due to climate change. These have impacts clearly on people, on societies, and have very high costs associated with them. So where are we headed looking into the future? If we could stop the world where we are now, perhaps we might be able to adjust to the changes that have already occurred. But as we look ahead, and this is a graph from the IPCC that is looking out to the end of the century, to the year 2100, it's showing that our business as usual case would result in increasing emissions, just as we've seen in recent years, along with increasing concentrations of CO2 in the atmosphere. So the current level of 400 parts per million by the end of the century could reach as high as 1,000 parts per million, a level not seen during the history of people on the planet. The consequence of those higher concentrations will be higher temperatures. We've talked about average temperatures. The average temperatures might be 3 to 5 degrees Celsius over the century, but not all parts of the planet will respond the same. Some parts, particularly in the northern latitudes, would see even higher temperatures. So think for a minute what that means. An average temperature of 5 degrees Celsius increase. The current average is 15, so that's more than a 30% increase. Think how your life would be affected today if all your days were 30% warmer. It might be nice in winter, but in summer, those pleasant days of 30 degrees would now be 40 degrees. How comfortable would that be? The 40-degree days, the rare 40-degree days, would be far more prevalent, and we'd see temperatures even higher than that on average. So the consequences of these higher temperatures actually are significant. Summary is that increases of warming are likely to be severe and pervasive across the planet. Again, the IPCC has documented the kinds of impacts higher temperatures would have. They include impacts on water, the availability of water for agriculture and for human consumption, impacts on ecosystems, impacts on food production, on coastal areas and flooding, and impacts on human health. And all of these impacts become more severe as the global average temperature increases. So what can we do about it? Let me talk in the rest of the period I have here about two options. One is called adaptation. Learn to live with it, adjust to the changes. Some adaptation actually is already occurring in countries that are close to sea level or in some cases below sea level. Here are two examples from the IPCC. The one on the left shows a high-tech solution, an engineered flood barrier in the city of Rotterdam in the Netherlands. The picture on the right shows a lower-tech option of planting trees to create a physical barrier in the South Sea Islands. Vulnerability and exposure to these kinds of impacts will vary around the world. Many of those impacts will fall on the people and countries that are least prepared to deal with them. The IPCC also has tried to document on a regional basis around the world what some of those future impacts might be. I don't expect you to read this complicated table. It's one that I can leave with you for further study. But the point is that science has documented at the very top the different types of drivers of climate change and tried to estimate for different regions of the world what some of the high impacts and risks would be. This slide shows their projected impacts for Europe, which are related to increased rainfall and drought. These studies have also tried to estimate the potential to adapt to changes, which are indicated by the bars at the very right. The point simply is that in some of the more developed Western countries, there is significant potential to adapt, at least in part, to some of these changes. Other parts of the world may not fare as well. In other parts of the world, the ability to adopt may be limited or not exist at all. In all of these cases, the things that are of interest to you all, especially social and economic systems, will play a key role in determining the future resiliency and the risks of climate-driven impacts in different parts of the world. So let me talk next about the second option, which is to reduce greenhouse gas emissions, an option that is typically called mitigation. The framework for this set of options actually goes back to the convention adopted in 1992, where all the nations of the world called for stabilizing greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Now, these are clearly words that they don't have any specific requirements for people to actually do anything. And yet, when one looks at the implication of trying to stabilize atmospheric concentrations, instead of concentrations going up, we want them to level off. Those implications are profound. The other question that was unanswered at the time was, what exactly do we mean by dangerous interference with the climate system? Over the decades, the consensus that has emerged in political discussions as well as scientific discussions is that no more than a 2-degree Celsius rise in the average global temperature is the nominal threshold that we will not want to exceed. The most recent agreement in Paris last year sets a much more ambitious goal, a stretch goal that is currently being looked at by the scientific community. But if we go back to the 2-degree limit and ask, well, what does it take? What would it take to limit the increase in global temperature to 2 degrees Celsius? If we work backwards, that means the concentrations in the atmosphere would have to be stabilized and limited to about 450 parts per million. Remember, we're already at 400, so that's not far from where we are now. And in order to limit the concentration to those levels, the key message is that the emissions that we are currently putting into the atmosphere would have to be reduced not by a little bit, but by a lot, by 50% to 85% by the middle of this century, by 2050. So big reductions are needed in emissions. Why such large reductions to stabilize the climate? It's mainly because, as I mentioned earlier, these pollutants, particularly CO2, are very stable and not easily or quickly removed by natural processes. So they remain in the atmosphere for centuries or more. That means that to stabilize atmospheric concentrations, emissions have to be reduced dramatically. The best analogy I can think of would be a bathtub. Imagine you have a bathtub that's being filled with water and you want to stabilize the level. You want to keep the level from rising. This particular bathtub, like our atmosphere, has a very small drain. The water isn't leaving very easily. So if you want to stabilize the level in the bathtub, you've got to reduce the water coming into the tub to match what is going out the drain. Otherwise, the level will still be rising. That's the situation we're in now with CO2 and other gases. So how can we get these big reductions in emissions? There are basically four types of levers. This is a simple representation of that. Emissions tend to grow because population grows, more people using more energy, because people are getting wealthier, the GDP per capita is going up.
And then the third factor of energy.
Per unit of GDP, per unit of wealth. And we're also doing that using fuels that have CO2 associated with energy use. The first two measures, population growth and GDP, are measures that are politically very sensitive. And for that reason, it's the last two factors that have been the focus of a lot of attention. These last two factors depend strongly on technology. Typically, computer models of global and national energy systems are used to find the combination of measures that can achieve these emission reductions at the lowest cost to society. And what comes out of these analyses are the following general insights. We need technologies and social systems as well. First, that can reduce the demands for energy in all sectors of the economy. We also especially need technology that use energy more efficiently. We waste a lot of energy in virtually everything we do, and more efficient technologies can give us the things we desire with less energy and fewer emissions. We also need technologies to produce and use energy sources that have low or no greenhouse gas emissions. Renewables, for example, such as wind and solar, are commonly discussed. And potentially, we also need technologies that can capture and sequester the CO2 emissions that are currently associated with fossil fuel use at power plants and large industrial sources. This would be a bridging technology to deal with the fact that we are using a lot of fossil fuel now, and if we need to reduce emissions quickly, switching to other sources is not going to be quick or cheap. A technology to deal with those emissions and put them deep underground where they do not enter the atmosphere is another option. All of these things are going to require major new investments, but those investments also represent opportunities for sustainable economic development, for example, in energy efficiency measures and other green technologies that are of growing interest around the world. One last topic then is how government actions influence technology deployment and innovation. The role of government in all of this is critical. Government actions and policies I've categorized into two types. One that we often call technology policy options, things like research and development, various incentives, tax credits, feed-in tariffs, as well as education and training. All of these things are carrots. They are incentives that are voluntary and intended to help and speed innovation and technological change. Many of these policies have been very important already. Here is just one example of government incentives in the United States that have played a key role in the growth of renewables, such as wind, for example. But history is showing us that those voluntary measures are simply not enough. In addition to carrots, we need some sticks, what I've called regulatory policy options. These are things like taxes on emissions, cap and trade programs, and various types of technology-based standards, portfolio standards, and performance standards. These are sticks that are not voluntary, they're mandatory, and can act both as incentives to force both innovation and technological change. These kinds of policies already have had major impacts on energy efficiency and emissions across a wide range of technologies. Let me show you just a couple of examples. This is a complicated slide, but it's one that has a nice story. This is the story of refrigerators, which in the 1970s was the most energy-consuming appliance in a typical household. The middle line that looks like a mountain, the blue line in the middle, shows increasing amounts of energy up till about 1972, when the state of California in the U.S. imposed a requirement that you could not sell refrigerators unless they met efficiency standards similar to the best technology on the market. Later, there are federal standards in the U.S. that have made similar requirements. And what happened, as you see, is that energy use came down. It came back to where it was many decades ago. And the other impact of that, which is shown in the lower line in green, is that innovation produced refrigerators that were not only using less energy, but were also less expensive. That lowest line shows the cost of the refrigerator. And at the same time, the red line on the top shows the size of refrigerators. They were getting more efficient, cheaper, and bigger. Here's another example of how regulations have forced changes in technology that have reduced energy use and emissions. This one is for automobiles. These are efficiency standards in the U.S. for automobiles that began back in the 1970s. Efficiency improvements have reduced already by a factor of 2 the amount of fuel it takes to drive a unit distance. The standards that we are looking at over the next decade or two will make even larger improvements. One other set of examples, the requirements for deploying renewables have brought down the cost and price of wind power and solar power as we see them being expanded in countries around the world. So where are we today? Over the last couple of decades, there have been a number of agreements that have covered increasing percentages of global emissions. Today, actually, about 2/3 of global emissions are in countries that have some type of an agreement to limit those emissions. At the same time, commitments in these agreements to large emission reductions are still largely lacking. Nonetheless, it's a recognition by governments that the problem exists, and it's a first step. Let me close with 2 promising new developments that occurred at the end of last year. One that I think you're all familiar with was the agreement in Paris last December to a new set of emission reduction commitments. The Paris Accord was one in which virtually all nations of the world, for the first time, agreed to binding commitments for what are called nationally determined contributions to greenhouse gas emission reductions and measures to achieve them. This means each country decides for itself what it can and wants to do, but everybody does something. The good news is that that agreement is now in place. The commitments that countries have made in this first step are not nearly enough to get us where we need to be, but it's a beginning. The other part of the agreement is that every 5 years, countries have to develop new plans to cut emissions beyond the previous levels, and those will be monitored and hopefully result in substantially larger reductions over the next couple of decades. The other part of the agreement involved rich countries helping developing nations by providing initially up to $100 billion a year in financing by 2020 and increasing the amounts after that. And then there was a long-term agreement that in the last part of the century, we would try to limit greenhouse gas emissions to activities that can be absorbed naturally. The other agreement coming out of Paris was something called Mission Innovation. 21 countries pledged to double their public spending on energy research and development over the next 5 years. That's important because advanced technologies can reduce the cost of mitigation strategies significantly. This is a map of the different types of research and development activities that different countries propose to subsidize. All of these also present increased opportunities for economic development through innovation. So let me close by asking the key question, what will the future bring? Let me suggest that first, the Paris Agreement last year is an important step in the effort to mitigate climate change because it's the first time that all the nations of the world agreed to start taking measures. There is still, though, a need for strong policy drivers to reduce emissions not by a little, but by a lot, and to spur innovation and deployment of clean and sustainable technologies. At the same time, the need for adaptation and more effective social economic systems also are needed to reduce climate change impacts. So a lot will depend on future climate policy developments. We'll be following that and tracking that. So watch this space for further updates. And thank you very much for your attention. Muchísimas gracias.